In this video, we're going to look at non-gradient search methods. At least one of the techniques is built into MATLAB. And what I would say at the outset here is good optimization is the kind of thing that gets covered in fourth year or grad school. If you really want to know the details of optimization, it is something that is very math intensive. There are some experimental sides to it as well. You'll see in computer science, you'll see in various engineering disciplines. But at the end of the day, to really understand what's happening, you have to have some strong background. There are any number of methods that are out there for optimization. And the reason they all exist is because for somebody's application, one of the other techniques, all the techniques that existed up until then, didn't work very well. So someone came up with another way to tackle the problem. There's many more algorithms than the ones here. The challenge is to find one that's well suited to your particular problem. By and large, the kinds of problems that we'll see in this class can be tackled by either the MTHE that we've seen already, or using the one we're about to see next. There's a method called the Simplex Method, which is meant to be a generic hunch your way down to the bottom of a function approach. It has a lovely graphical idea behind it where you have some starting points, and if you think that downhill goes in this direction because these values all go down, then you kind of jump over to here and build a new triangle. There's all sorts of fun background to this. At the end of the day, you just need to know that in MATLAB, the implementation of this simplex method is called fmin search. The idea is that it's going to be versatile and hot swappable with the fmin as we'll see in the code here. When we look at optimization code, here's what we ran last time: function, initial value, options, fmin search as a function, x0, options. And this is fantastic because it means you can try one optimizer, see how it performs, tracking how it improves things over iterations. And if it's not doing what you want, you try another optimizer. Swap out fmin for fmin search and see how it does. So we're going to take a quick look at fmin search in the MATLAB help, and then we'll look at W10.2 and use fmin search instead. So we're going to comment this line out, copy it first, and we'll replace that with fmin search, and that should be the only thing we need to change. We'll take a quick look at the help menu though, and we'll see find the minimum of unconstrained multivariable function. That's exactly what we want. Minimizing a function by trying different x values. X is a vector. This is exactly the same as fmin. There are details on the algorithm and all sorts of other information, but at the end of the day, we just want it to search. So let's try it. And because we have the display routines built in, that's interesting. This feels very different than the search for the fmin. This, in some ways, looks most like the blind hill climbing or blind hill dropping down approach to optimization. It doesn't feel very precise, and that's because it's not based on calculus techniques. It's based on having these points kind of limp across each other, recognize when we've gone into a direction that takes us up instead of down, turn a corner. It's much more heuristic is the word that search algorithm people would use. But at the end of the day, it still ends up in a local minimum. Let's do another search, say starting at -1, just to see how that plays out. And to show that it's basically doing the same job. And we run that. So we start here, it does a bit of searching, goes faster and faster until it realizes it's gone too far, then it backs up, and then starts doing an interesting little grid search almost here until it hones in on that local valley in the bottom. We can also see the tracking here, the values are around 77, which is close to our minimum, and it does kind of stall a little bit. There's not a lot of improvement for these last 10 or so steps compared to the first few steps where we're really making progress. And we see how many iterations it took. This is definitely taking longer than the other algorithm. The reason you might want to use this instead of fmin is that it seems to take longer in this example. But the hope is, and it's only a hope until you actually try it in practice, is that it's more robust complicated, and especially not necessarily complicated, but non-differentiable or non-smooth optimization functions or objective functions. And smooth, of course, is the property of having a derivative value that doesn't change very quickly. And if f min u and c is depending on derivatives, then bad derivative properties will make this have a hard time. Whereas f min search doesn't care so much about that. It's a little slower when things are smooth, but it also might handle cases that are not smooth. A kind of example that is definitely not going to be smooth, the relationship between the inputs and the outputs, is the truss design. As you change the locations of joints, sometimes one beam is the one that's going to break, and then as you move joints around, it might be another beam that starts being the most fragile or where the trouble spot is. That kind of thing is indicative of a breakdown in derivatives. You don't get a continuous change or a smooth change, and so f min u and c can sometimes have some trouble with that. f min search can be a little more robust. But the nice thing about all of this is that you don't need to know in advance. You don't need to be able to predict, is one method better than another method, because you just try one, and if it's not working so well, or you don't know if it's working well at all, you see how well it's converging, and then you swap it out and try the other method and see how quickly it converges. Try some different starting values. At this stage, and in practice for most optimization routines, this is a guessing and checking kind of approach. Try the best numbers you have for the initial location, and then experiment with which optimizer seems to give you the best bang for your buck, the most efficient search for local improvements after that.